Ja, nu må vi ikke sådan kritisere, når jeg siger noget, der ikke er helt rigtigt om de der kemiske ting, ikke?
Jeg sidder og fortæller, at jeg har jo læst det danske resumé, så jeg ved, hvad det går.
Ja. Og det er store sager. Jamen, så held og lykke, Line. Nå, okay, nu ved du, hvad det handler lidt om.
Du skal sidde på de forreste rækker.
Nej, præcis. Det er også de farligste. Hej så.
Jeg smuttede ud om dig, ikke? Jeg ved ikke godt
Nej, det ved jeg ikke. Jeg så, at Matula kom med nogle eksamensopgaver, så tænkte jeg, at du har nok glemt dig. Hej så. Tak.
Det er verdens bedste fremlægning.
Ja, selvfølgelig godt det. Ja. I hvert fald den bedste om biogas, du har hørt i år. Ja. Nå, er du klar?
Ja.
Her over styr.
Det er vi. Jeg kan se, du er også helt klar.
Jeg er også helt klar.
Det er godt, du har den her.
Ja. Jeg tænkte, det var meget god lige til os, hvis der var nogen, der sagde, hvad mener du lige med? Ja, det er et godt spørgsmål. Et øjeblik.
Helt klart.
Jeg synes ligesom, der mangler sådan et par stykker af de vigtige der, jeg ved ikke.
Nå, så skal vi vente på det, men kan vi ikke bare starte, så er det bare ærligt, så kan de ikke spørge noget, fordi jeg er.
Det er ikke. Ja.
De var der lige før. De skal nok komme.
Ja. Nå, og det kommer nu, kan jeg se. Hej. Hej så.
Det var bare en grav.
Tak. Jeg tror, at det er meningen, I skal sidde der. Men, I måtte gerne flytte jer, men, sagde Vivi, men hun havde sat vandflaskerne der. Ja. Ja.
Det er højt op.
Det er rigtig højt op.
Højt op, når man selv står og kigger, ikke?
Ja, det er svært at pege præcis, når man har sådan noget. Skal ikke ryste for meget på hånden, når man peger. Det går. Giver du sådan en 5-minute warning eller et eller andet?
5 minutes warning.
Altså, jeg ved sådan, når der er bare sådan en diskret.
Jeg skal nok. Der er også ordet deroppe.
Ja, det er rigtigt.
Jeg skal.
Ja. Jeg kører bare.
Du kører til nummer 40, jeg går ud fra.
Ja. Jamen, den fylder lidt mere nu, så jeg regner med, at den nok bliver 45.
Kom op, jeg skal nok.
Lad os se.
Vil du gerne have 5 minutter før?
Ja, måske.
Du når 45.
Ja. Altså, hvis du ikke kan se, at jeg er kommet til concluding remarks, så må du gerne lige...
Så skal jeg nok. Okay.
Ja. Ja.
Vi starter. Welcome to this PhD defense. I'm Henrik Jacobsen. I'm a professor here at D2 Management, and I've been following the work we're going to hear about, and I'm very happy to hear that you are ready to present about this great topic. I would like to welcome the assessment committee. We have Erik Algren from Chalmers in Göteborg, and we have Trine Bomsma from University of Copenhagen, and Stefan Røbke, he is from Management as well as we are. He's heading the committee. And of course, I very much want to welcome you, Ida Græsted Jensen. And you are presenting your work here, Value Chain Optimization in Biogas Production. For today, we have a program where Ida will present 45 minutes from her work. We will have a 5-10 minutes break after that. And from then on, we will have the assessment committee asking questions, presenting their comments to the work. So we will have a debate. If anybody wants to, from the audience, wants to raise questions or comments to Ida, you are requested to give me a remark of that in the small break. So I would welcome you and let you introduce your work to the audience here.
Thank you.
So please.
Thank you. So my PhD was titled Value Chain Optimization in Biogas Production. And for those of you not so familiar with biogas production, it's something about this. So we have a biogas plant here producing biogas out of waste products, or mainly manure, and some extra substrates that are added to the manure. So today I will talk, first I'll give you an introduction to the problems. I'll give you a motivation for why it's relevant. I'll tell you about my research questions, my goals, and the papers I've done. Then I'll dig a bit deeper into what I call paper C, which is about optimizing the value chain. First giving you an introduction, talk about network flow optimization, simplification of transportation costs, modeling of stepwise linear cost functions, and then the results of the paper. Then I'll talk about the remaining papers, just briefly talk about the conclusions of the papers. And then for the concluding remarks, I'll talk about my contributions and further work. So first to the introduction. So in the Danish energy system, we have a high share of wind energy, which gives us a need of an alternative dispatchable energy source that can be used for electricity production when the wind is not blowing. When this project started, there was a goal of 50% of all manure had to be used for biogas production in 2020. This is actually not a goal anymore, but anyway, it seemed really, really unlikely to reach this goal, because in 2012 we had approximately 4 petajoules of biogas production. If we had to use 50%, we had to reach 13 petajoules of production. The Danish Energy Agency made this prediction of, they had a number of applications for investments in biogas plants because you were granted support for the investments, and they ranked the investments whether or not they were very likely or unlikely to succeed. And as you can see here, the goal could only be reached if they included the unlikely projects in the evaluation. So you could ask why projects are unlikely, but maybe it has something to do with the feasibility of the plants not really being sure if they can make it or not. So that was what we wanted to consider. So why even consider biogas? Of course, it has some advantages. It's a renewable energy, and it has storage opportunities. So we can store it when, as I said before, when the wind is blowing. We do not want to use it for electricity production, but then we can use it later on when it's needed. Then for the greenhouse gas emissions, it's potentially greenhouse gas emission reducing because of the manure that is added to the biogas plant. We can redistribute nutrients both locally and nationally. So if we have a pig farmer and a cow farmer, the content of the manure regarding nutrients is not the same. So if we mix it together and then spread it on their soils, it probably will create a better fertilizer. Then, when you use this for as a fertilizer, you will even get a reduced smell. So if you just spread manure out on the fields, it's really, really smelly, but not as smelly if you do it through the biogas plant. Then we have that it's produced out of waste products. So for instance, the manure, which you cannot really use for that much else. And then we have job creation in rural areas, because as you saw, the biogas plant is really, really big. So we both need people to transport all the input and to operate the plant. So my PhD was part of the Biochain project, which was a research project consisting of a total of 5 work packages. Some were looking into the emissions in the value chain, all the emissions here. Some were looking into how much biogas we could get out of the different input types, and some looked into the substrate, the digestate coming out of the production. How good is it for the soil? So now to my dissertation. So my first research question was about how to ensure economic feasibility in the value chain. And that was, of course, to get more projects through. Then the second research question was about profit allocation in the chain. So how should the profit in the chain be distributed among the different owners participating? The last research question was about the energy system. So how should biogas be used? Then I had 3 goals as well. The first goal was to develop methods for ensuring economic feasibility in the chain. The second was developing decision tools. And the third one was to improve the modeling of biogas in energy system models. So I made a number of papers. First 3 papers in my dissertation is regarding research question number 1. Paper A is about integrating energy, greenhouse gas, and economic accounting. So my contribution to this was mainly on the economic accounting part. Paper B was a review of supply chain models in the bioenergy industry. And paper C is the one about optimizing the supply chain. The paper A, no, I cannot point anymore, paper A and paper C contributes to the goals of developing methods and developing decision tools as well, whereas paper B only mostly contributes to the methods, to identify what others has done, and to give me a chance of finding out what to include in my model here. So now for question 2. Here I made paper D, which is about why we see that that the biogas plants that are built now are choosing to upgrade, and how we can explain this by profit allocation. And then I have made paper E and paper F. The first one was about evaluating the impact of CO2 cost on biogas usage. And this paper F was about modeling renewable gas and fuels in the Danish energy system. The 2 last ones concerns research goal number 2 and research goal number 3. Yes. For today, I will focus mostly on paper C, because I believe this is where I made the biggest methodological impact. So that's what you're going to hear about now. So the purpose of the paper was to address the research question 1, how can we ensure economic feasibility in biogas value chains? And the objective of the model was to maximize the profit when we were producing biogas. And And I did this by mathematical modeling. So what is it that we want to decide on? That is investments in the biogas chain. What should we produce and what should we produce it on, and how big should it be, and so on. Then we had to decide on the inputs to the biogas plant. What should we use in the biogas plant? When should we use it? When should it be stored? How should we pre-treat it? And so on. And last, the output from the plant. What type of end products should we produce? And the input to the plant, the input to the model is the location of the plant. So I was given a location, a specific location in Denmark, and from this we had the amount of available input. Then we have some costs. We have investment costs and operational costs and so on. And we have some prices for the end products. And then some technical specification of the technologies. So how fast can we pre-treat a product, and conversion rates. Okay, so from the paper B, the review, we looked into what other people had included in the models, and I make this small graph showing what was included. So this is basically the full chain of biogas production. We have it from cultivation until end use, and as you can see here, a lot of people have considered transportation. Of course, everyone considered the plant. That's obvious. Not that many had included pre-treatment. To a lesser extent, storage before the plant was included, but after the plant, more or less, 5%, I think, had it included storages. So what I found from this was that I wanted to include the whole chain. And with the whole chain, I basically mean from we harvested until the end use. So the cultivation could be how much land should be used for a specific crop, but that's not part of the optimization. Then also the storages should be included. So because we want to use the biogas flexibly, we need to include the storages both before and after the plant. And then I wanted to set the time resolution as high as possible to capture the electricity prices, but also to capture the seasonality of the biomasses. Okay, so this is my value chain. So what we have here is, first we have two different input types. So I made a other input type and a manure type, which can be sent to pre-treatment. The pre-treatment of the inputs could, for instance, be briquetting of straw or chopping of sugar beets. And then from here, it can be sent to a storage and then to a plant where we get the digested out that can either be sold at a market or sent back to the livestock farmer to be used for as fertilizer. From the plant, we also have the biogas production, where we have possibility of upgrading the biogas to natural gas quality, and it's done by removal of CO2. It can also be sent for methanation, where we, through electrolysis, add hydrogen to the mix and thereby create more methane, so it ends up with a quality close to that of natural gas. From the methanation, we also have heat production because of the electrolysis. From the plant, we also have the possibility of using it in a boiler to produce heat, or in a CHP technology where we produce both heat and power. Yeah. So to do this about the time resolution, I didn't really divide it, but I set two different time resolutions in the different parts of the chain. So on the output side, to capture the fluctuations in electricity prices, I chose an hourly time resolution. And on the input side, I chose a weekly time resolution to capture the seasonality. One could say that I could have used the same time resolution for the whole model, but then the size of the model would increase really much because the week should then be in hourly time resolution as well. So that was why I chose this. So I also defined some challenges that I needed to overcome. The first challenge was this about mass and energy losses. So in the chain, we can have some losses when we do the different pre-treatments of the inputs, but we can also get changes in the biogas potential. And when modeling the chain, so the mass and the biogas potential doesn't necessarily change at the same time, so we had to handle it separately. Then we have this about the storages that I needed to consider. We have the transportation costs, which I wanted to represent close to reality, but not as a really detailed transportation part of the model. So to limit the transportation running time of the model. Then I needed to consider diseconomy and economy of scale. I'll show you why in a minute. And figured out how to do this. The first two parts were done by network flow optimization. The transportation costs I tried to simplify so I could reduce the running time. And then the diseconomy and economy of scale, I modeled that using stepwise linear cost functions. So first for the network flow optimization part. So the network flow optimization in general consists of a graph network. So we have a set of nodes. We have a set of arcs between the nodes. And then we have decision variables describing the level of flow on an arc. And a general minimum cost network flow problem is the following. We want to minimize the cost on an arc. So it's multiplied on how much of flow we have on the arc, and then we minimize it. Then we have a constraint saying that the flow going out of a node minus the flow going into the node is equal to a parameter b, which in the interior of the graph is 0. The last constraint is a level. So the level of flow on an arc has to be between a lower and an upper bound. So in my value chain model, I made a graph network in 4D and in 2D. So on the input side, I needed to model the input type that I use, the process that I'm in at the moment, the time period, and then the energy content. And on the output side, I only had the process and the time periods. So I made this small example segment for sugar beet, so it's not exactly how it's done for a sugar beet, and it's not in 4D as you can see, because that's kind of hard to draw. So, so this is just in 2D for you. So as you can see here, I have input in time period 1 and time period 2 from the farmer. It can be sent to a storage or for pre-treatment. Then it can stay in the storage in a number of hours, as well as in the in a number of weeks, and also for the pre-treatment, it can stay in storage. Oh, sorry, it can just stay in the pre-treatment. Yeah. So when we want to model mass loss in this type of network, we take. So this is an example for the storage in the sugar beet chain, where we have in time period 3, we have some red arcs going in, and we have some blue arcs going out. So the modeling of mass loss basically says that every one of the red arcs should be multiplied by the mass loss, eta, and then be equal to the sum of the blue arcs going out. And that's just a simple change in the flow conservation constraint, where we just multiply eta on the last part, on the left-hand side of the first constraint. Now for the energy loss, that was a bit more difficult for me to draw for you. So I tried to make the same network as you saw before for sugar beet. So this is for the first time period. We have the energy content index E here. So we have, it starts at 100%. Then I say that it's reduced by, with 2 percentages down to 98. Then reduced again 1% for each time period it stays in storage. 6 down to the pre-treatment and 1 again here. So now it looks really simple, but now I added for time period 2. We have an input here, so it's the same numbers, but shifted 1 time period. And now for the arcs going down to the pre-treatment facility directly from the farmer, we have this network. Before, I don't think you counted the arcs before, but there were 21 arcs before, and now we have 38 arcs. So as you can see, that the size of the graph increases rapidly when you want to include energy content. So now to the modeling of storages. So again, I tried doing something with red and blue arcs. So let's say that we have a maximum process time of 5 weeks in storage, so you cannot stay longer than 5 weeks in this storage. First of all, the graph, when I made it before I sent it to the mathematical model, I ensure that that I do not make more nodes than necessary. So here you can see the last node in the storage is 5 weeks after it came in. And then again we have something about the red arcs. The summation of the red arcs times the mass loss has to be less than or equal to what leaves again out of the blue arcs. And then again I have to reduce it by a mass loss here. So there will happen something with the mass losses that ends up with being, so that what's leaving here is actually less than that what enters if you do not take mass losses into account. Yeah. So now to the simplification of transportation costs. So why is it even necessary? First of all, data availability. So when you want to cover a huge area, you might not have the exact placement of every farm in the area, but you might have an idea of approximately how much sugar beet you have around your plant. And then again, about running time, that if we include it too detailed, it will just increase the running time of the model. So my idea when I made this was to aggregate the data in concentric circles. As you can see here, we have the biogas here, and we have concentric circles around the plant with different radii here. And then we have, I calculated the average distance for each annulus. And annulus is basically kind of the donut here. So this is an annulus and so on. And then I calculated the transportation of the full amount in each annulus using the average distance. And when doing this, you get something similar to this one out. So if we let S denote the S annulus, then H of S denote the amount available in the S annulus. And as you can see, the cost increase when we want to go out. And this is this economy of scale. And that leads me to the next part, modeling of stepwise linear cost functions. So to model this economy of scale, we have to do something else than we usually do when we just put numbers into our model. So I had to consider this a bit. So it can be done by introducing a new type of variable, the WS, which are variables representing the amount transported from annulus S. So it's how much is transported here, how much is transported here, and so on. And then AS are the slope of the cost function in annulus S. So the slope in here and the slope here, and so on. And the resulting model is the following. We want to minimize the cost, and that's done by taking how much is transported in each annulus times the cost of transporting in each annulus, and then adding it up. And then we state that the amount transported from an annulus cannot be more than is available in the annulus. And this is really nice, but it only works because Ws minus 1 is cheaper than Ws. So the function is convex, as you can see here. So we want to fill up the first parts here before we fill up out here. And then to economy of scale, that is the opposite, so it's a concave function. And we want to do this because for the investment costs and also the operational expenditures, they're usually economy of scale. So it gets cheaper the bigger we build per unit, the bigger we build. For modeling this, we have to, again, divide the model up in sections here. So we have some different breakpoints denoted by k, that's the breakpoints. And then I have x hat, which is the x value at the breakpoint. Okay. So this can be modeled using the so-called SOS2 variables, which are variables that can be between 0 and 1, but at most 2 of those variables can be non-zero. And the 2 non-zero variables has to be next to each other, you could say. So it should be modeled over an ordered set. So down here, it would mean that for lambda k is then the SOS2 variable denoting the proximity of x to x hat, call it. So we could not have a lambda 1 and a lambda 3 being non-zero because then they're not next to each other. So it could be lambda 2 and lambda 3 being non-zero. So the idea is that we use the lambdas to multiply them on the cost on the connected breakpoint. So if we had again lambda 2 being non-zero, it would be multiplied on the cost of x hat 2. And then we have that the sum of these variables has to be equal to 1, and that it's SOS2 variables. So it means that if, again, lambda 2 and lambda 3 were non-zero, there could be, for instance, a half. It would mean that we would have a solution in the middle between x2 and x3. And then you would take half of this cost and half of this cost and add them together, meaning that you would get exactly the cost in the middle. That's really hard to point at. But so that's the idea. So now I applied the model to something. I learned that you also have to do that, so I needed to find a small example case study to do it with. So I used the placement of the plant that you saw on the second slide in Mobjerg, and then I included 3 different input types. I included manure, sugar beet, and straw. I included 5 upgrading possibilities, including the methanation. I had 1 boiler type, and I had 3 CHP plant technologies. Yeah. I made the model in GAMS using a Cplex solver on this fancy computer, so nothing special. So for all my problems, I had a running time of less than 21 minutes, but I had a huge model. I had O of the number of arcs, linear variables. I had O of k, denoting the number of breakpoints, SOS2 variables, and then I had O of a constraints. So it was really big, so it was really necessary to cut out all the unnecessary arcs I could imagine. So that's why I made a really, really clever Java program to only write up the necessary arcs. My preferred input was manure and straw, so I did not use sugar beet. but I used a storage of straw, so it could be fed into the biogas plant continuously over the year. Another thing that we could see was that it was chosen to use methanation in all scenarios but 2. So I tested with setting the natural gas price to half it, to multiply the electricity price with 1.5, to set a low heat demand, combine all of these 3, to cut the subsidy for methanation in half, and then to use the subsidy in half plus a low natural gas price, and that's where something happened. As you can see, the objective decreased really fast, and the same thing goes for combining the subsidy low and the electricity price set high. So the reason for electricity price having an effect on methanation is that you use electrolysis for doing your methanation and thereby use electricity, so you have to pay for that electricity. The last one was combining the low subsidy with the low heat demand, and there you can see that only the amount of heat produced were changing. And of course also the objective. Then I could see that I used the storage of biogas and heat. So this is only showing that we use the storage of biogas. So here, first of all, you see the electricity price is shown with black. So you can see that it increases in some time periods. The same time periods just before that, you can see that we have a storage charge here, and a really big one here. So they see a huge electricity price, so they wait with producing, with doing the electrolysis till after this high number. So the conclusion of the paper was that it's possible for us to ensure economic feasibility in the case study, but the problem is sensitive to change in regulation of methanation, electricity prices and gas price, but only if they're combined in some way. We could also see that we were able to capture the challenges that we wanted to, and as a bonus for today, I also wrote that it's easily extended with more input types. Because the model is there, we just need to change the data. Okay. For the remaining papers, I promised you I will only present the conclusions of the papers. So for paper A, which were it was a giant paper made together in the Biochain project of 11 authors, where we tried to integrate the evaluation of how much energy we get out, the greenhouse gas emissions, and economic accounting. As I already told you, I contribute to this part. So for this paper, I developed the transportation cost simplification. But what we got out of this paper was that it was not possible to find an overall best solution where we could both get positive energy, greenhouse gas balance, and a positive economic solution. We also saw actually from this paper that sugar beet was not economically feasible, but it was given a number of assumptions on pre-treatment and stuff like this. So it did not optimize anything. Paper B, I already told you the 3 first points. So not many papers cover the whole chain. Storages are important, and the time resolution should be considered. The last one, stochasticity, might need to be included. So depending on, for instance, electricity price fluctuations and stuff like this, you might need to include stochasticity. What we saw from my results was that if we only changed the electricity price, it did not affect the solution. But you could consider other types of stochastic elements to include. So now for paper D, which was the paper about profit allocation. So in this paper, we applied 3 different profit allocation mechanisms after running the plant level model from paper C. And when we did this, we found, funny enough, 3 different allocations of the profit between the 3 owners that we included in the model. So first we have the livestock farmer. This is for our base case, which was the year 2016, where we had a low natural gas price. We found that the best solution was to do combined heat and power production. And what we can see here is that they all prefer a different profit allocation mechanism, which in the end might result in them not being able to agree on anything. What you can further see is that for the plant, so except for the best solution he can get doing proportionality, these 2 mechanisms are actually worse than in this case, meaning that he might want to consider trying to decide something with an operating plant instead of a combined heat and power plant. So looking at the natural gas high thing, we can see here that both the plant and the upgrading plant would prefer to use a proportionality allocation method, and then it's more easy for them to agree maybe on this allocation. But as you can see, the livestock farmer is not as satisfied when this is done, which might explain why the livestock farmers are hard to involve in biogas projects. But this could explain why we want to upgrade instead of combined heat and power production. Okay, for paper E, looking at the impact of CO2 cost on biogas usage in the energy system, we saw that the biogas target could only be reached if we had a very high CO2 cost, and we had that the flexibility of biogas were not explored by the model, because it's modeled as just a fuel that can be used anytime they want to. For paper F, we had the modeling of renewable gas and fuels. So the first conclusion was regarding biogas is that we have biogas in all scenarios, but with no CO2 cost. We have the biogas is upgraded by CO2 removal, but in periods where we have a high natural gas price, in the scenario where we have the high natural gas price, it's boosted by methanation to obtain more biomethane to sell. And then we also saw that straw was in the mix when available. Okay, so for the concluding remarks, my contribution in this PhD dissertation was luckily that I were able to reach my goals. I had my first goal about the methods, so to develop new methods. I developed the method to combine mass and energy losses. I developed the method to simplify transportation costs, and I did this profit allocation between heterogeneous owners. For the research goal 2, I developed decision tools. So first, the plant level model from paper C, the profit allocation models from paper D, and then the model from paper A addressing the economic and environmental effects. The 3 first papers, the three first models would mostly be for investors in the biogas plants. So for instance, for the farmers, to consider if it makes sense or not. The last bullet here, inclusion of biogas and biogas production in energy systems models from paper E and F, would mostly be from an energy planning perspective. So the third research goal, biogas in energy systems models, to make a better modeling of this. For the first bullet point here, combining use of natural gas and biomethane in the technologies that are included in Balmoral. We did that because we can substitute the natural gas by the biomethane, but it's not included in Balmoral as it is today. And then the second one is inclusion of biogas production in Balmoral by the OptiFlow add-on. And then I made, as you have already seen, 6 papers. 3 of them are published. Paper C is published in European Journal of Operational Research. Paper A and E in the journal called Energy. I have 2 under review. The first one is paper B in Renewable and Sustainable Energy Reviews, and paper D in Energy Economics. We just got this back with a major revision, so it's hopefully on its way soon next year. And then I have 1 working paper, which is still a working paper, but we have decided on a deadline, I think, to be submitted in January. Okay, I have also a number of bullet points for further work. So this is actually really soon further work. It's about evaluating economic performance, CO2 reduction, amount of gas production, and flexibility of biogas production when you use different regulatory regimes in the plant level model. So see how you perform when you change the regulation. The second one is to include economy of scale on, I wrote some of the output processes, maybe all of the output processes, but it will also, I will also need to consider exactly what I include on the output side to reduce the size in order to be able to do it. Then something about a robust investment solution. So as you could see, if the natural gas price changes, and it will change, then maybe the solution you found in time period 2017 will not be the same best solution as in 2020. So it can be done by either extending the horizon of the model or making more sensitivity analysis to change the different parameters and see what do you think is the best after this. Then there is one point which I did not do, is something about the simplification of transportation costs and how much it actually affects the solution. So when I did the model, I just chose 5 kilometers as a good distance between the circles, but maybe we could see if changing it to 1 kilometer steps or 10 kilometer steps actually changes anything. When the project started, an idea was also to consider who should own what in the chain. And that was because what we see today is that it's different from biogas project to biogas project, who actually owns the biogas plant and who, if it's a farmer or it's like a company going in from somewhere else. So one could think that in the profit allocation model, you could consider also to add this element of who actually owns which costs in the model. And then the last one relates to the future gas project, which I'm supposed to work on when this is done, where they want to consider including the gas system when evaluating biogas performance in the energy system. So my last slide, that fits exactly. So as you can see here, in 2012, the production were not that big, but then something happened here. And as my model shows, we should consider upgrading our biogas, and as this is what the Danish Energy Agency believes will happen in 2020. So luckily, what my model thinks is the best solution is also the way it's supposed to go. Yes. And that was it.
So thank you for this great presentation, and I can see you did precisely on time, maybe 1 minute ahead, but that's really great. So we will take a short break now, 10 minutes, so we will start again, 5 minutes to 2. There will be a cup of coffee outside for those who want that, and when we get back, we will have first the presentations from the panel, questions, and after that, we have the 2 supervisors that are also welcome. We agreed on maximum 1 or 2 questions per person in that case. And if any one of you are also interested in raising a question, please tell me here in the break. After the whole program, we will have a reception in 426. So I guess you are all welcome there as well. And you had a comment?
Yes,
please.
it's a practical issue. There's no lights in the toilets. So if you want to use these toilets, bring light. Else, in the other buildings outside, you will find toilets. So it's very practical.
Okay, thank you so far.